Linears, curve sketching. Curve sketching. Right. We discussed that maxima and minima, right? And some questions also we discussed, right? Some more questions we need to discuss. Right. Now the next application of this differentiation is the this curve sketching part. Right. People, before going to this curve sketching part, we must understand some properties of curves. Right. So the first thing there we have to do today is, people, the concavity of a graph. Right. They are write down subheading as concavity. Concavity, right? Okay, concavity, right? Right now, I'll consider a graph. Now, this is our y-axis. This is our x-axis. Now, consider a graph like this. Consider a graph like this. Or another graph like this. This is x-axis. This is y-axis. The graph is this now. Okay. Now, taking these two graphs, now I am going to construct tangents to this graph. Tangents. Like this, huh? Yeah. Tangent means a line that touches the curve at a point like this. Here. This is a tangent drawn to this point. Here. This is another tangent drawn to this point. Here. This is another tangent drawn to this point. You can see, once we keep draw this way the tangents, here we draw this two. Right? This way. When we draw tangents to the graph, you can see this graph and this graph both graphs lie above the tangents. Here above the tangents. Here graph lies above the tangents. Then such graphs are called as, people, graphs of concave up. Graphs of concave up. Graphs of concave up. Okay. Those graphs are called as, people, graphs of concave up. Concave up. Concave up means the graph lies completely above the tangent. Similarly, we can draw another two graphs like this. Take these two graphs, x-axis, y-axis, this way. People, like this. When we keep drawing tangents here, in this case, you can see the graph lies completely below the tangent. Here also, when we keep drawing the tangents like this here, the graph lies completely below the tangents. Then such graphs are called as, people, graphs of concave down, right? This is concave up. Graphs of concave up. Here, graphs of concave down. Right. Concave down graph means graph lies completely below the tangent. They are the two basic concavity shapes that we must understand at the beginning of this part. Okay, concavity. Okay. Yeah, then write down people under this concavity, and write down in that concavity graphs of concave down and concave up. Graphs of concave down and concave up. Right, draw these diagrams. Graphs lie above the tangents. Here. Graphs lie below the tangents. Below the tangents. Right, draw these two diagrams. Draw these two diagrams. Right now, people. Right now, yeah. Now, people, I'll take a few graphs to step the next one. Another few graphs. Have we finished this? Right now? Right. So I erase this now. Okay. Now, consider a graph like this. When I consider a graph like this graph, of course, you learned in our previous lesson under maxima and minima. This is this kind of graph. In this graph, of course, this point we identified as stationary point. And this graph is called as point of inflection. Point of inflection. The other possible shape for this point of inflection with the stationary point is this. Can you remember? I told this is called as a point of inflection. Here we have a stationary point. While we were discussing about the stationary point only, this point of inflection I discussed. People, now here, this is called as the station point, right? And sometimes called as the point of inflection. This is called as point of inflection because of this reason. Now I'll keep drawing the tangents to the graph somewhere here. You can see when we draw the tangents, right? Now here the graph lies below the tangents, concave down. And when we draw the tangent to the graph at this stationary point, the tangent crosses the graph like this here. Tangent crosses the graph. Thereafter, if I keep drawing the tangents to this graph, you can see this way, the graph is concave up. Now, from here to here, graph is concave down. Graph lies below the tangents. This graph lies below the tangents. After this point, the graph lies above the tangents. Then from here to here, graph is concave down. After that, graph is concave up. So you can see this is the point where the concavity of the graph changes. At this point, the concavity of the graph changes. From here to here, concave down. From here to here, after that, concave up. The concave down graph changes to concave up graph at this point. That is why this point is called as point of inflection. So therefore, this point is point of inflection as well as it is a stationary point. Stationary point means dy by dx is 0. Okay. So therefore, this is of course a point of inflection as well as stationary point. This is also the same here. When we keep drawing the tangents from this end here, now the graph is concave up. When I draw the tangent to this station point, that tangent crosses the graph like this. Thereafter, when we keep drawing that tangents, you can see graph concave down. Then again, the concavity of the graph changes at this point. At this point, dy by dx is 0. Dy by dx 0 means stationary point. So therefore, this point is stationary point as well as this point is called as the point of inflection because at that point only the concavity of the graph changes. On the left of the point, graph is concave up. On the right of the point, graph is concave down. So therefore, this point is called as point of inflection. People will take another graph here. Now, if I consider graph this people, suppose this way I am going to consider graph x-axis, y-axis. Here, take this graph. This way a graph. Consider a graph like this. Right? People, when you consider this graph, now I am going to sketch some tangents to this graph. Yeah. I draw the tangents like this here. Tangents above the graph. That means graph below the tangents. Here. When we keep drawing like this, the tangents, people, you can see one occasion the tangent crosses the graph. Here, tangent crosses the graph. After that, here, tangents like this. You can see, starting from here up to here, the graph lies below the tangents. Then from here to here, graph is concave down. After this point, when we keep drawing the tangents, you can see the graph lies above the tangents, therefore concave up. From here to here, concave down. After that, concave up. Therefore, at this point, again, the concavity of the graph changes. So therefore, this is called as what? Point of inflection. But here, this point is not a stationary point. In the earlier two examples, that point, a point of inflection as well as stationary point. But here, the dy by dx is not zero. Therefore, this point is not a stationary point, but it is a point of inflection. Right? So therefore, point of inflection can exist this way too. Now, if I consider another graph, people, this way. X-axis and y-axis like this, huh? This way graph. When we consider this graph, see here again, when we keep drawing the tangents like this here, right? You see, we can draw the tangents. You can see from this end to here. When we keep drawing the tangents, the graph lies above the tangents. The graph is concave up. After that, concave down. Here, the concavity of the graph changes. Okay. So then this is another point we can consider as a point of inflection. So therefore, people, the point of inflection can exist basically in this way, four ways, right? These are the tangents. Right, these are the tangents. So therefore, people, the way of defining the points of inflection is the point where the concavity of a graph changes, right? That is how we define the point of inflection. Understand? Okay, right. Now write down another subheading as people, point of inflection. Write down points of inflection is subheading. Okay, right. Now write down a sentence like this. Right, now asking a question, so is the graph name point of inflection or point on the graph name point of inflection? Yes, point on this graph. This is a graph. On this graph, there's one point at which the concavity changes. That point only we define as the point of inflection. For the graph, we never say point, no, right? This point only we say point of inflection on the graph. Right. Okay. Now write down like this. Points of inflection. Write down. Write down the point on a graph at which the concavity of the graph changes. The concavity of the graph changes. Is defined as a point of inflection a point of inflection. Right. We will draw this diagram. 4 diagrams in the same line like this, huh? Small diagrams. Try to draw this. Here, point of inflection. Point of inflection, right? Here it is this. Right, to the left of this, concave down. Right of this, concave up. Here concave up. Concave down. And here concave down, this side. Concave up. Here concave up. Concave down, right hand side. Okay, right, complete the knots. Right, if you draw this in the same line, people, I supposed to draw another few diagrams exactly below them. Right now, people. Right. But now I am going to construct another graph. Right. I'm going to draw the graph of dy by dx against x. What do you mean by that? Dy by dx means gradient, no, people? Yeah. You know, when we consider a graph this way, the gradient of this graph at a point we measure like this. For instance, if I need the gradient of this graph here, at that point to the curve, we construct a tangent like this. Okay. This is a point P. at which we construct a tangent to the graph. Then this tangent makes an angle, suppose this theta with the positive x-axis. For this angle theta, we can find tan value. This tan value is called as the gradient of the curve at the point P. Okay. Now you can very clearly understand this angle, this way increases, theta increases until 90. Then theta acute angle, no? Then tan theta positive. As theta increases, you can see the gradient increases. That means gradient means dy by dx. Understood? So therefore, now if we have a curve like this, when we keep drawing the tangents like this, here the gradient is given by tan of this angle. Gradient means, people, we know dy by dx. We learned that. Gradient means dy by dx. Dy by dx gradient, and this gradient is defined as tan theta. Okay. Now we keep drawing like this, the tangents, people. This angle increases. When the angle increases, theta increases means tan theta increases. That means gradient increases. That means dy by dx increases. Okay. Similarly, if the graph is like this, similarly, if the graph is like this, when we need to find the gradient at a point here, we have to construct a tangent there. That occasion, you know, people, this is the angle we have to take. This is the angle we have to take to find the gradient of this. But you can see this time this angle is obtuse angle, more than 90. That occasion, for an angle which is more than 90, the tan value, when you find, it is in the second quadrant. No, second quadrant tan is negative. Therefore, the gradient is negative. I think, right, I told this before too. When the gradient is negative, right, to find the exact gradient, I told you to take what? This angle. To take this angle and take its tan value and put minus sign before. Like this. Minus tan alpha. To get the gradient of this point. We put minus sign because the gradient is negative. Its size is given as, right? Right, people? Right? Size is given by tan alpha, then minus tan alpha. Then you can see, when we keep drawing this way, people, tangents here. When you draw the tangents like this, you can see this angle decreasing here. This angle decreasing. That means alpha decreasing. Alpha decreasing. Alpha decreasing means tan decreasing. Okay. Then I suppose to take some value here. Somewhere here tan, people, angle alpha greater, no? Then the gradient I write minus alpha greater. Then the tan alpha will get greater value, like 4. That is somewhere here, suppose. For instance, no? When I come to somewhere here, alpha, this angle smaller than the earlier, but still having minus sign. Alpha going down means tan alpha also going down. Then suppose that tan alpha for the small angle now, the answer is 3. Then we get gradient as minus 3 somewhere here. When you come to somewhere here, people, again this angle, that means alpha furthermore going down. If alpha going down means tan also going down. But before we have minus sign. Like this, we have minus 2. So you can see, if we have a graph like this, people, right? If you have a graph like this, then you can see, people, the nature of the gradient here. Graph is like this here. Gradient is, right, here, this is the number line 0. Somewhere here, gradient 4. When you go to right, somewhere here, gradient minus 3, right? somewhere here, gradient -2. What happens, people? When we go along the positive x direction to the right, the gradient having minus sign going towards 0. Going towards 0 means, people, gradient increases, no? Compared to -4 and -3, -3 greater than -4. -2 greater than -3. Then when we move along the x-axis to the right, the gradient of this graph with minus sign increasing towards what here? Increasing towards 0. Understand? So therefore, this property and this property, right, we have to keep in your mind. Now we are going to draw dy by dx, the graph of dy by dx against x for each of this graph. And that is very important to us to get the condition for the concavity or the point of inflection at a point. Understood? Okay, right. Now I'm going to draw the dy by dx graph for this. Dy by dx graph for this x-axis, right here, dy by dx. Dy by dx means gradient, people. When I consider this graph, people, here, gradient is positive. When we go this way, that tangent makes the angle with positive x-axis, that angle decreasing. And finally, at this point, the tangent is horizontal, angle is 0. Okay? When we go this way, people, gradient, especially the angle when we consider this way, people, this angle, while we are moving this way along the graph this way, the angle decreasing. Angle decreasing. Okay? This angle is decreasing. Then what happens? The angle is acute angle. Gradient is positive. Okay? Angle decreasing means tan decreasing. That means when we move this way, people, the gradient is decreasing through positive values. Why? Why do we say positive value? This angle, when we construct tangent, that tangent makes with positive x-axis acute angle. That's the reason. So therefore, up to this point, when I consider the sizes of dy by dx, gradient positive. And that positive gradient gradually decreasing up to what? 0. If I take this point as x equals a, suppose this point has the x coordinate a, right? X equals a here. Until the point x equals a, the dy by dx, if I mark here, somewhere here, a positive gradient, somewhere here, positive gradient, but earlier gradient. And this, when we compare, it is less, right? Like that, gradient decreases. And here exactly, gradient 0. Why? We said what here? Station point. Thereafter, to the right of this, what happens? This tangents make great angle with the positive x-axis, great angle. If the angle is greater, tan greater, then gradient increases through positive values again. Reason? That angle tangent makes with the positive x-axis acute. Through acute angle, it is increasing, then the gradient increases. So then the other dy by dx, if I mark on the right of this point, this way we get some points. Right now, people, dy by dx means gradient of this graph. Now we take x value and corresponding gradient we measure. That point we mark like this. Then when we construct, people, a graph like this is the graph we get. This kind of graph we get. Right? People, now gradient of this graph is given by dy by dx, no? Right? Gradient of this graph is given by dy by dx. That means we have to differentiate this to find the gradient of this. Like that, to find the gradient of this graph, we have to differentiate this dy by dx again with respect to x. Then when we differentiate people, this dy by dx again with respect to x, we get second derivative of y. That is d2y over dx2. Therefore, gradient of this graph is the second derivative. You can see people, from here to here, the gradient of this graph negative. The second derivative is negative. After this, the gradient of this is positive. Gradient of this graph means second derivative. Second derivative positive. Therefore, to the left of this A, second derivative negative because this graph has negative gradient. To the right of A, second derivative positive because this gradient is positive. So now when you compare this and these people, to the left of this A, the graph is concave down. Yeah, graph is concave down. To the left of this A, second derivative negative. Come to again this. To the right of this A, the graph is concave up. To the right of this A, second derivative positive. People, can you see a particular relation? The relation is this. If a graph is concave down here, in that interval of x, second derivative is negative. If the graph is concave up, here after this A, this graph is concave up. The corresponding second derivative is here. Second derivative means people, the gradient of this graph, positive. Then if the graph is concave down, second derivative negative, concave up, second derivative positive. That is the relation by these graphs we can draw. Okay, right? Now similarly, if I construct here, again you can see that property. And not only that, people, another one relation I have to remember here. Exactly at A, you can see we have a point of inflection. At that A here, if I construct a tangent, that tangent goes along the x-axis. When the tangent is parallel to x-axis mean, people, when the tangent constructed to the graph parallel to x-axis mean, the gradient is 0. But in this graph, its gradient means the derivative of this, no, that is second derivative. At this point, second derivative 0. At this point, second derivative 0. Why? When you construct the tangent, that will be along the x-axis or parallel to x-axis. That is another important property. What is that property, people? At x equals a, if there is point of inflection, at that x equals a point, second derivative is 0. Right? Second derivative is 0. That means at the point of inflection, second derivative becomes 0. They are the important things here we can draw. Understood, people? Right? Here we can draw. Okay, no? Right. Similarly, people, if I construct dy by dx graph against x, this axis I can take as dy by dx. Here x-axis. Right. From here to here, you can see, people, what? Gradient negative. Okay. Gradient negative. Gradients negative. But when we keep drawing the tangents from here to here, that tangent makes smaller angles, decrease in the angle. That occasion, you know what? Gradient is negative, increases up toward 0. So then, if we construct the dy by dx graph, in this case, what kind of graph you get, people? Here, the negative dy by dx axis. Right? Then you get what there. At x equals a, suppose here x equals a point. Then somewhere here gradient negative. See somewhere here point we get. Somewhere here gradient negative, but that angle is smaller, no? Then the minus sign we have anyhow, and then value is less. Then this way. We said what? When we go this way, through minus values, gradient going to 0, no? Then this way we get some points. Exactly here, x equals a, gradient 0. After that, again gradient negative, what? Decreasing. Like this we get points. Right? This way we get a graph. People, now, in this graph, to find its gradient, we have to differentiate this. When you differentiate this with respect to x, we get second derivative. See here, the gradient of this graph is d2y over dx2. We have to differentiate this to find the gradient of this graph. But you know, from here to here of this graph, gradient is positive. Here, this graph, gradient is positive. That means on the left of A. On the left of A, this graph concave up. Again, it verifies. When the graph is concave up, in that interval, the second derivative positive. Go to right of A. This gradient negative. In this graph, the gradient negative. Gradient in this graph means second derivative. Second derivative negative. That's well obvious. But on the right of here, A, this graph is concave down. And also at x equals A, here when we construct a tangent to this graph, that tangent will be moving along x-axis. Given the gradient 0. At this point of this graph, gradient is 0. Gradient 0 means the gradient of this graph is given by second derivative. Second derivative is 0. At x equals A, second derivative is 0. See here, at x equals A, there is a point of inflection. Again, it verifies what? At the point of inflection, second derivative is 0. And if the graph is concave down, then in that interval, second derivative is negative. If the graph is concave up, in that interval, second derivative is positive. For these two graphs also, people, in the same way we can construct what? This graph dy by dx, and we can discuss this same property. Okay. Then people, right? You have now drawn these 4 diagrams. No, below that, write down. Let's construct. Write down. Let's construct the graphs of dy by dx, the graphs of dy by dx against x Right. Now come to exactly below this, draw this one, below this, draw this one. Right. Now I am going to draw this one also. First draw these two. right? Under this, draw this one. Under this, draw this one, right? Yeah. Now, shall I draw the dy by dx graph for this? Now, you can see the gradient of this graph is negative, right? Up to here. Now, I am going to measure here the gradient. Now, when we draw the tangents will make great angles while we are coming this way, right? The tangent makes great angle with the left hand side of x-axis. That means what happens, people? Gradient will take minus, angle gradually increasing means the value decreasing like this. And coming to the maximum angle here, no? Then the points come in like this here. Thereafter, when you pass this one, again, once we keep drawing the tangents make like this and angle decreasing, but still negative. Angle decreasing means with minus sign value decreasing means, people, that is increasing like this, no? Yeah, like this. Then the second derivative graph is this. At x equals a, again, the lowest point coming. Then the gradient of this graph is what, people? The derivative of this second derivative, d2y over dx2. You can see from here to here, the gradient here, negative. And then from here to here, the graph is concave down. After this point, the gradient of this graph is positive. Gradient of this graph means second derivative positive. That is after A. After A, when we consider this graph, what is that? Concave up. If the second derivative is positive, here concave up. And also, people, when we construct here a tangent at this point, you can see this tangent will be parallel to x-axis, right? Then here the gradient is 0 of this graph. The gradient of this graph means second derivative. Second derivative is 0. Where? At x equals a. At x equals a, this graph has point of inflection. That again verifies at the point of inflection, second derivative is 0. There also now I can construct the last one. Right? There what happens? Gradient positive. The angle increasing. Therefore, gradient increasing. We get it like this here. This is x equals a point. Come to the maximum. And thereafter, still the gradient positive and angle the tangent makes with x-axis decreasing. Then the tan value decreasing like this. This is the graph we get. At x equals a, gradient maximum, and thereafter decreasing. Like this, huh? Right. Now you can see, people, in this graph, the gradient is positive up to here. That means second derivative positive. Up to A. Then up to A, when you move along this graph here, look at this. Concave up. After that, second derivative negative. Second derivative negative. Here, concave down. And exactly at x equals a, when we construct a tangent to this point, people, that tangent will be parallel to x-axis. Gradient of this tangent now 0. That means second derivative 0. X equals a, we have point of inflection. So therefore, by these 4 graphs, people, they verify 2 things. If the graph is concave down in that interval of x, second derivative negative. Graph is concave up in that interval of x, second derivative is positive. At the point of inflection, second derivative is 0. These are the things, people. By these 4 graphs we can take. Right. First construct them and we'll write 1 knot. Right now? Shall we take down a note there? Okay. Now we can write brief note like this. Have you finished drawing this? Write down, people. Write down. The second, write down the second line graphs, the second line graph, that means this graph I'm saying, the second line graphs, or the graphs below, whichever, never mind, the second line graphs show the variation of the gradients within bracket write down dy by dx, within bracket write down dy by dx of the first line graphs. Of the first line graphs. Write down the gradient of second line graph or second row, also correct, second line graphs is given by d2y over dx2. d2y over dx2. Right. Now, people, you have to mark some more things here. At this point, d2y over dx2 0, no? Here, d2y over dx2 negative. This range, d2y over dx2 positive. Here, positive. Here, negative. Here, it's 0. Right? Here also, second derivative 0. Here, second derivative negative in this interval. Here, positive. Right, here also you can come at this point, what can say? Second derivative 0. Second derivative positive here. Here second derivative negative, this interval. Mark them 2. Okay, yeah. Now write down paper under this. Write down. By this graph, we can determine the following. We can determine the following. Number 1, write down. Number 1, write down. At the point of inflection, at a point of inflection, the second derivative is 0. Write down, that is d2y over dx2 equals 0. Number 2, write down. Number 2, write down. If a graph is concave down, if a graph is concave down, in an interval of x, the second derivative in that interval is negative. In that interval is negative. Third one, write down. Third one. If a graph is concave up, if a graph is concave up, if a graph is concave up, in an interval of x, in an interval of x, the second derivative in that interval is positive, is positive. Is positive, right? Okay, therefore people, at a point of inflection, remember second derivative is 0. At the point of inflection, second derivative is 0. If we have a point of inflection, the corresponding second derivative at that point, 0. But the people, the converse is not true. What's the converse? If second derivative is 0, that doesn't say there exists point of inflection at that point. Right? Converse is not true. Right? If there's a point of inflection, definitely at that point, second derivative is 0. If the second derivative is 0, it doesn't say there's a point of inflection. Sometimes there can be, sometimes not. The reason is, we can very easily, people, verify that thing by using this simple example like this. When you consider the graph of y equals x to the power 4, the graph of y equals x to the power 4, when I consider this one, y equals x to the power 4 graph, when you consider, you know people, y equals x squared graph. Y equals x squared graph we drew, it is a minimum graph passing through the origin. This we discussed where in the quadratic equation lesson. Right? This graph also, people, we have what? Same shape. Right? Only thing is, people, now here when x equals 2, what is y? 4, no? Here when x equals 2, y, what do you get, people? 16. Then these two branches coming closer when you draw this one. That kind of graph is coming like this. The graph of this also this. You can see the graph is minimum graph where at x equals 0. At x equals 0, graph is minimum graph. Okay. And also you can furthermore see here, when we construct tangents here, right? The graph is concave up, the whole graph, concave up. The graph lies above the tangents, concave up. You can see no change of concavity throughout the graph. Always the graph is concave up. Right. Now see, differentiating this twice. dy equals x power 4, no? dy by dx is what? 4x cubed. d2y over dx2, what? Bring this here, 12x squared. 12x squared. People, when I put x equals 0 here, second derivative value at x equals 0, what can I say? Put 0 here, 12 into 0 is 0. What happens? Second derivative at x equals 0, we have 0. Second derivative 0. But what do we have? Do we have a point of inflection? No. at x equals 0, this is the point on the graph now. This point, a minimum point, not point of inflection. For this point to be point of inflection, before this point and after this point, the concavity of the graph should change. No such change. The graph is concave up throughout it. So that is why I told people at the point of inflection, second derivative is 0. Right? If second derivative is 0, nobody can say definitely that point is point of inflection. The converse is not true. Understand? So therefore, in order to show there exists a point of inflection, first thing is this. You have to show second derivative is 0. That is not sufficient. In addition to that, on the left of that point and right of that point, you have to show the second derivative takes opposite signs. If before positive, after negative. If before negative, after positive. Right? Then only we can easily say at that point there exists one point of inflection. See here, second derivative 0. But after this point, before this point, concave up, second derivative same sign, positive. No point of inflection. So therefore, if we need to show for a particular given graph, it has one point of inflection. First thing is this. We have to take the second derivative and we have to show the second derivative is 0 at a certain x value. Not only that, it is not sufficient. Before that x value and after that x value, we have to furthermore show the second derivative will take what? Opposite signs. Then only we can very easily prove at that x value there exists a point of inflection. Understood, people? We'll take down that as a note. Write down that as a note. Right, write down like this as a note. Write down. At a point of inflection, the second derivative is 0. Write down. But the converse is not true. But the converse is not true. But the converse is not true. Write down. That is though the second derivative is 0, at a particular point on a graph, it does not say that point is a point of inflection. Right, start from new line. Therefore, in order to show a point on the graph, a point on a graph is a point of inflection we have to first show the second derivative at that point is zero and before and after this point, the second derivative takes opposite signs. Second derivative takes opposite signs. Second derivative takes opposite signs. Opposite signs. Second derivative takes opposite signs. Right, we'll come to one example, people. Show that the graph of y equals x cube has a point of inflection at x equals 0. At x equals 0. At x equals 0. Right, people? Now, we can say here y equals x cube. First, we differentiate this dy by dx, 3x squared. Second derivative, d2y over dx2. 2 comes here, 6x. Second derivative value at x equals 0. 6 into 0, 0. Then at x equals 0, second derivative is 0. Now we are sure what? Before 0 and after 0, second derivative should take opposite signs. Now I am going to take this. Second derivative, d2y over dx2, no? I need its sign. The point of inflection is at x equals 0, no? Now I need the sign of second derivative before 0 and after 0. First, x less than 0. X less than 0 means x is negative. Second derivative answers this. When I put negative value for this 6 into negative value means this is negative, therefore second derivative is negative. Next one, second derivative. Sign after x0, x positive. Right? Put here like positive value like 3, 4 like that. 6 into positive is positive. Second derivative is positive. Here. Before 0, second derivative negative, after 0, second derivative positive. Therefore, at x equals 0, there's a point of inflection because x equals 0, second derivative 0. Understand? Therefore, at x equals 0, graph has a point of inflection. A point of inflection. Understood? And people, this point of inflection, you can see first derivative dy by dx at x equals 0. Put 0 here. 3 into 0 is 0. Dy by dx is 0. At x equals 0, dy by dx also 0. So this time, this point of inflection, not only just point of inflection, but that what? A station point also. Understand? So that situation, people, is really, if we draw the graph of y equals x cube, the graph is like this. Graph is like this. Here, point of inflection is this. Dy by dx also they are 0. Right? To the right, you can see second derivative positive means concave up here, this way. To the left, concave down here, this way. This is the graph of y equals x cube. Understand? So this is the point of inflection as well as stationary point. Okay, there are points both satisfying point of inflection and stationary point. Okay, so this is y dx. Right, draw the graph of y equals x cube also like this. This is the point of inflection. Point of inflection as well as this is station point. Stationary point. Both qualities this time it has. Stationary point. Dy by dx 0, second derivative also 0. You know the station point we learned no before? Maxima or minima point. Here, second derivative 0. Right? The points where dy by dx are called as stationary points. Stationary points. Okay. Now, people, we move to the curve sketching part. Now, one part of that we discussed here. Some more important things are available there to discuss. Right. Right now, yeah. Now we'll come to the important properties of curves. Right. Right. Shall I erase this now? Okay. Now. Right. Now, people, I am going to draw now a graph which has all the properties. Right. Say the graph like this. The graph I'm going to, yeah, this is the graph, right? This way, we have vertical dotted line. This way, horizontal dotted line. Right. Now, the graph is this first part. This thing, it goes this way. And Right, people? Right. This way, a graph. I'll take another point here. Right. This way a graph, right? See here, a graph I drew this way, right? This is also enough. I'll take this one now, right? A graph like this. We'll take a graph like this. Okay. This is y-axis. This x-axis. I'll take this x coordinate is A. Here y coordinate is B. People, when you consider this graph, some properties you can see in the graph. Okay. Right. Now you can see at x equals A, when we go to meet the graph, this graph, this one, become parallel to this dotted line. That means this dotted line and this graph become parallel. That means they meet at infinity. That, in other words, people, when we go closer to this A, this height means y coordinate, no? Height going to infinity. And when I come to this end, to this A, again this graph and the line, the vertical dot line become parallel. That says, when we come to this A on the left, on the right to this A, this y value going to negative infinity. People like that. When we go to a particular x value from either side, if the y coordinates of the graph going to plus infinity or minus infinity, people, we say at that x value, the graph has vertical asymptote. Vertical asymptote. Vertical asymptote. Vertical asymptote. For example, suppose here, if I consider graph like this, y over y equals 1 upon x minus 2, like this. When you put x equals 2, what happens? 2 minus 2, 0, 1 over 0, this goes to infinity. So therefore, at x equals 2, only this happens. Therefore, we say what? At x equals 2, graph has vertical asymptote. So therefore, the first thing is, people, when we draw a graph, we have to check whether this graph has vertical asymptote or not. How to check that? In order to have vertical asymptote, definitely the equation of the graph should have a denominator. And there should be x values that denominator becomes 0, as here. To find that x values, we can equate the denominator to 0. When we equate this denominator x minus 2 to 0, x will be 2. Therefore, at x equals 2, there is a vertical asymptote. So therefore, to find the x values at the vertical asymptotes, what we have to do, people, in the given equation of the graph, go to the denominator, equate that denominator to 0 and find x values. Understand? At that x values, people, we have what? Vertical asymptote. So therefore, first of all, we have to check that. Right. And people, you can see, when we go to right hand side along the x-axis this way, this y value of the graph going to what? B. When we go to this way here, along the x-axis to right, this y value of the graph gradually going toward this B. And from this end, when we go to negative infinity of x, is a negative infinity direction, no? negative x-axis. When we go this way, people, look at this. Graph is, y value of the graph is going to be. Okay. That way, people, when we go to positive infinity direction and negative infinity direction, the y coordinate, the height of the graph is the y coordinate, no? If the y coordinate goes to a definite real number, there we say the graph has horizontal asymptote. The graph has horizontal asymptote. Understand? Now, for example, if I take something like this, here y equals, see here, x plus 2 divided by here x squared. Okay. I'll take that one, yeah, like this. Okay. X plus 2 divided by x squared. In this case, I am going to take limit x going to plus or minus infinity, right? Why? Because we have to discuss the y value while we are going to positive infinity direction of x and negative infinity direction of x. That occasion, the y should get what, people? Real number as the answer, right? So see what happens here. I can take x out from the numerator. You know how to take the limit of this. 1 plus 2 upon x. Here, x squared. This and this you can cancel down. Right. Now we can put infinity for these places. What do you get? 1 plus 2 upon infinity divided by infinity. Right? Now, people, I will take this as x. Then much easier to consider now. This x and this x will cancel off. Then here we have 1. Right now, I took x out. Here now, not x squared, x only. Here, take x out. 1 plus 2 upon x. This x out and this denominator x we can cancel down. We have now 1 plus 2 upon x. The denominator is 1 now. Now 2 upon infinity is what, people? 0. Then y is 1. Look at this. Y is 1. As x going to plus or minus infinity, this y going to 1. Y going to 1. That means what? When we go along the x-axis to the positive infinity direction and negative infinity direction, the y coordinate going closer to what, 1 from both ends. Then that is called as the graph has horizontal asymptote. Understand? Horizontal asymptote. So therefore, when we draw the graph, we have to check whether this graph has horizontal asymptote or not. How to check that? To check this, people, we have to take the limit of x positive infinity or negative infinity of the equation of the graph. Understand? Right. Next one, people, you can see here, this point is minimum point. The minimum point we discussed in the earlier part. Right? Maxima and minima under that. Right? This is the minimum point. Minimum point is, people, a stationary point. So when we draw, people, the graph, sometimes there are stationary points. How to find the stationary points? We define the station points. The stationary point can be a maxima or minima or point of inflection. Understand? At the stationary point, people, we know what? First derivative is 0. So therefore, to find the stationary points, what we have to do is, the given equation of the function, the graph, we have to differentiate. And we have to find dy by dx. And you know, at the stationary points, dy by dx equals 0. So therefore, the function we get for this dy by dx, we have to equal to 0. Then we get some x values. At those x values, there are station points, maximum, minimum for a graph. That also we have to consider before drawing the graph. Station points. How to do this now? Differentiate the function, take dy by dx, equate that expression to 0 and find x values. those x values are the x coordinates of the station points. That also we have to consider. People, the other thing is here. You can see here, when we keep drawing the tangents here to this graph like this here, you see when we keep drawing the tangents. One occasion, people, here, the tangent crosses the graph. Here, this is that place. From here to here, graph is concave up. After that, graph is concave down. When you keep drawing the tangents, this way, people, you can see that. Then this point is not, people. This point is point of inflection. Then the graph can have a point of inflection too. Then we have to check that also. Understand? How to find that? To find that, we have to take the second derivative and equate that second derivative to 0. Then we get x value. At that x value, there can be a point of inflection. We told now, people, though the second derivative is 0, that doesn't say always we have a point of inflection. After finding that x value, we have to furthermore show the sign of second derivative before that x value and after that x value, second derivative sign is opposite. Then only we can say at that x value, there exists a point of inflection. Finding this all information together, people, including them into the graph, we have to draw a clear graph. Then only we get the full marks for that. Understand? Okay. Yeah. Then people will discuss these properties, and thereafter we can go to question discussion. Right? I'll take this point as, people, A, this point as B. Now write down like this. Consider the following graph. Consider the following graph. Right. People, draw this graph. Draw this graph. This x equals A, this y equals B. Right. Then shall we take down a knot? Right. First draw this diagram. Mark that point A, point of inflection, point B, the minimum point. Right. Write down like this. Write down. Number 1, write down. Write down. When we approach to TO2, when you approach to x equals A, along the x-axis, from both sides, we can see the y value of the graph goes to plus infinity and minus infinity, plus infinity and minus infinity. Then it is said, SAID, then it is said the graph has vertical asymptote, ASYMPTOTE, vertical asymptote at x equals a. At x equals a. Write down to find the x values, to find the x values at the vertical asymptotes, equate the denominator of the function of the graph to 0. To 0. Write down here a second point. Write down second point, number 2. When we walk alone, x-axis, when we walk along the x-axis to the plus infinity and minus infinity, to plus infinity and minus infinity, we can see the y value of the graph, approaches to simple b, the y value of the graph approaches to simple b. Then it is said, the graph has horizontal asymptote at y equals b. At y equals b. At y equals b. Write down to find the y value of the horizontal asymptote take the limit x going to plus or minus infinity. Take the limit x approaches to plus or minus infinity. Take the limit lim x arrow plus or minus infinity. On the right hand side of the function of the graph. Function of the graph. Right, people, number 3, third point. Write down. The point capital B in the graph, the point capital B in the graph is a minimum point. Is a minimum point. Write down. It is a stationary point. It is a stationary point. To find the x values, to find the simple x values at the stationary points, solve the equation dy by dx equals 0. Dy by dx equals 0. Solve the equation dy by dx equals 0. Write down, people, fourth one. The point capital A on the graph, the point capital A on the graph is a point of inflection, is a point of inflection. Is a point of inflection. Write down. To find the x values at the points of inflection, to find the x values at the points of inflection, solve the equation, d2y over dx2 equals 0. d2y over dx2 equals 0. Right. Now, people, these are the things we have to follow before sketching a graph. Now, today we go to sketch a graph. Right? Yeah. Okay, people. Right, people will come back to the lesson. Now take the tutorial, second tutorial I put to the group, second tutorial, question number 5. Right, question number 5 in the second tutorial. There you are given the question like this. Okay. Question number 5, part A, given like this. For x not equal to -1, let fx equals x plus 2 upon x plus 1 squared. This way you are given. Show that f dash x, the derivative of fx is given by this. Right. We have to differentiate this. How to write f dash x? F dash x means the first derivative, right? So here you have to follow. This is u, this is v. Right. First we have to square this. X plus 1 square of this means 4. V squared. And bring this v here. V du by dx means the derivative of this. It's 1 minus. Keep this x plus 2. And now we have to differentiate this. How to differentiate this, people? First we have to start from 2. 2 times x plus 1 to the power 1. Derivative of x plus 1 is 1. Right. Now here we can take x plus 1. Here also x plus 1. X plus 1 is common. Take x plus 1 out. Open the bracket here now x plus 1. Here when you take x plus 1 out, 2 times x plus 2 we have. Remove the bracket multiplied by 2. Minus 6 into 2 is minus 2x. Minus 4. Divided by x plus 1 to the power 4, right? This and this we can cancel. We get power 3 there. Then we get f dash x. Here simplify this. Minus 2x plus x is minus 6. 1 minus 4 is minus 3. Divided by x plus 1 cube. Take this minus sign out. X plus 3 divided by x plus 1 cube. F dash x is this, right? First answer is okay, no, people? This is also true when x not equal to -1. Why, people? When x equals -1 here, what happens? -1 plus 1, this is 0. 0 power 3 is 0. Something divided by zeros, infinity. Infinity has no meaning. Infinity has no meaning. That is why. Here also the same reason, given x not equal to -1, right? Okay. Given that for x not equal to -1, f double dash x is this, where f double dash x denotes the second derivative of fx. Indicating asymptotes, turning points, and points of inflection, sketch the graph of y equals fx. Hence, find the range of x. The graph is concave up and concave down. Okay, right. Now, people will see how to take this. Right. You know, when we draw a graph, as I told you, first we have to find vertical asymptotes, horizontal asymptotes, stationary points, points of inflection. There's a particular rhythm of answer in these things. I'm going to give them step by step. So you have to do this way whenever you answer this kind of question, wherever, right? So for those steps, you get marks. So therefore, definitely you have to follow those steps to get the full marks, right? Now, first thing is, we are given this fx means really y, people, right? Fx means y. Y is x plus 2 divided by x plus 1 squared. F dash x means dy by dx. I write like that. F dash x stands for the dy by dx. Dy by dx just now we found minus x plus 3 divided by, right? Minus x plus 3 divided by x plus 1 cube, right? Right. Second derivative also given us. F double dash x means second derivative. Second derivative given as 2 times x plus 4 divided by x plus 1 to the power 4. This we given the second derivative. Right. Now, first thing is, people, the point of vertical asymptotes, right? We'll find the vertical asymptotes. Right. Okay, people. Right now, I erase this part, right? I think you have finished this, huh? Okay, first one you can write vertical asymptotes. Right, vertical asymptotes. For vertical asymptotes, you know, people, for vertical asymptotes, we told this denominator of the function we have to make it to 0, right? For vertical asymptotes, x plus 1 perfect squared should be equal to 0. X plus 1 perfect squared equals 0 means x plus 1 equals 0, x equals minus 1. Our vertical asymptote is at x equals minus 1, right? Now, secondly, horizontal asymptotes we have to find. Horizontal asymptotes. Horizontal asymptotes. For the horizontal asymptotes, people, the right hand side of this, we have to take the limit going to plus or minus infinity. Understand, right? Yeah. Y limit x going to plus or minus infinity. X plus 2 divided by x plus 1 squared. I take x out from the numerator, 1 plus 2 upon x. Take x out from this. Since here we have square, once this x comes out, that will be x squared. And this is now 1 plus 1 over x to the power 2. You can cancel down this x with 1x here. Now put plus or minus infinity for this x. What do we get there? 1 plus 2 upon plus or minus infinity divided by here plus or minus infinity. 1 plus 1 upon plus or minus infinity perfect squared. Right. Here 2 divided by infinity, this is 0. Therefore, this is 1. Right. Here plus or minus infinity. Okay. 1 upon infinity is 0. We can bracket 1 now. Right. Now what do you get here? Y equals 1 upon plus or minus infinity. 1 upon infinity is 0. 0 has no sign, therefore horizontal asymptote is y0. That means when we move along x-axis towards plus infinity and minus infinity, the y coordinates of the graph coming closer to what? X-axis. That's the meaning of y0. Right? Right. So now we have here vertical asymptote x equals minus 1 correspond to fm dot y equals 0. Now people, next one, we have to find what? Stationary points, right? For stationary points. For stationary points, dy by dx should be equal to 0. dy by dx should be equal to 0. Understand? dy by dx is this. Once we equate that to 0, we get like this, minus x plus 3 divided by x plus 1 cube is equal to 0. For the fraction this to be 0, definitely this numerator must be 0. X plus 3 should be equal to 0. X is minus 3. That means the exponent of the station point is minus 3. Now at that point, it has x coordinate and y coordinate. Both no y coordinate also we have to find. To find the y coordinate, that x equals minus 3 we have to put here and here, right? Now you can find that y coordinate. When x equals minus 3, y minus 3 plus 2 minus 3 plus 1 perfect square. Minus 3 plus 2 is minus 1, minus 3 plus 1, minus 2 perfect square. Y equals minus 1 upon 4. Then what is the stationary point? Minus 3 minus 1 upon 4. Station point is minus 3 minus 1 upon 4. Right, stationary point. Minus 3 minus 1 upon 4. Right. People, now, next. Points of inflection. You know, for points of inflection, what is the condition required? Second derivative must be 0. Right? So then our next point is that. For points of inflection. What can say? d2y over dx2 equals 0. Second derivative is this. This is 0. 2 times x plus 4 x plus 1 to the power 4 equals 0. This fraction 0 means, people, this numerator 0. X equals minus 4. Right. The points of inflection occurs at x coordinate minus 4. That point there is a y value, no, people. Y coordinate also there, no. For any point x and y, both coordinates available, no. To find the y coordinate, what we do, this x minus 4 we substitute here. Y. X is minus 4 plus 2 divided by minus 4 plus 1 to the power 2. Here numerator minus 2, denominator, see here, minus 4 plus 1 is minus 3. Minus 3 squared is plus 9. Minus 2 by 9. Therefore, the point of inflection, people, occurs at minus 4 minus 2 by 9. Point of inflection is what? The point is minus 4 minus 2 by 9. Right, this way, people, we have to gather the required informations. Right. Okay, people, now after this, After finding this way, all the information, vertical asymptotes, horizontal asymptotes, stationary points, points of inflection. After finding these informations, we prepare two tables. We prepare two tables, right? That two tables you have to definitely show in your workings. For them, you get marks. Understood? Right. Yeah. The two tables are this. Okay. Right. Before preparing these tables, people, I'll tell you what are the information that we have to include the table. Right. First, we have to draw a line like this. Okay. On that first line, the x values you mark are the x values of vertical asymptotes and the x values dy by dx 0. That means stationary points. Right. Vertical asymptote -1, station point -3. Yeah. Then -1 here, -3 here. Then remember, in the first line, you mark what, people? Only the x values. What x values? The x values at the vertical asymptotes and x values at the stationary points. Station point, x value is -3, no? Right. After marking this, you get an idea to prepare the table. To prepare the table. Table now very easily you can prepare. Right, -3, -1 here. Now this is the table. Very easily you can find the table here. Right. In the table, this interval, left of -3, that means x less than -3 interval is this. This interval, x greater than -3, less than -1. This interval, x greater than -1, we write it like this here, x greater than -1. Here the important thing is, people, on either side of this vertical line, we have the -3, -3, -1, -1. That way we prepare. By preparing this way the intervals of x, people, we are supposed to find the sign of dy by dx in each interval. Okay, sign of dy by dx here. We are supposed to find dy by dx sign in each of these intervals, right? Like this. Right. Now, this is our dy by dx. In this dy by dx, we have to substitute, right? Take in a value from this interval for x, right? Here, dy by dx, I write here. It is -x plus 3 divided by x plus 1 cube, no? Right. Now, in this interval, x less than -3, we need the sign of dy by dx. For this, what we do, we take any real number from this range and we substitute for x. I take like -10 here, -10 plus 3, -7. That -7 and this minus sign plus, numerator plus, denominator, -10 plus 1, -9. -9 to the power 3 is minus sign. Numerator plus, denominator minus. Plus by minus is minus. So therefore, this is minus. Minus. Take this interval. Between -3 and -1, select a value for x. Take -2. Put that pair here. -2 plus 3. It's 1. With this minus sign, -1 numerator. -2 plus 1. -1. -1 to the power 3 is minus. Minus, when you divide, we get plus. This is plus. Right? X greater than -1. Take a value on this interval, 0. Put that here. 0, here 0. Here -3, here 1, then minus. We get the sign like this. Right. We get the sign like this. Okay. Now people, by having these signs, you can very easily determine the shape of the station point. We said the station point occurs at -3, no? You know the station point can be either minimum or maximum or point of inflection. We'll see what is its shape. Very easily you can determine that shape. X equals -3. Here, on the left of the gradient, minus. Minus gradient means like this shape, no? Minus gradient line when we do, this is how we have to do that, no people? On this interval, gradient is positive. There's a line when we draw like this, we should have that line. Exactly at x -3, the gradient is 0. The horizontal line like this. Then people, according to this shape, we should have a curve. What is this curve? Here the curve should be like this, people. It is a minima. Then using the first derivative test, we can determine the shape. Minimum station point is there. According to the shape, gradient negative, 0, positive, minimum shape. We discussed that. Right. Okay, that's all. Minimum. Right? Okay. Next one. Next table, people. First table is okay. Then for this table, you get marks. Second table, again, we draw the line. On the second line, people, again we mark x values. This time the x values are the x value at the vertical asymptotes and x values at the second derivative become 0. First line we had what? Vertical asymptotes x values. Second line, vertical asymptote x values and second derivative 0. First line, vertical asymptote x values and dy by dx 0 x values. Second line, vertical asymptotes x values and second derivative equals 0 x values. Second derivative equals 0 means point of inflection, that is -4. And then we have to put -4, vertical asymptote is -1. -1, -4. -1, -4. They are the x values we have to put in this. Now, accordingly, you can what? Construct the table. There, we are supposed to find the sign of second derivative, d2y over dx2. This interval, x less than -4, -4, x less than -1, -1, x this way. Okay. Now, second derivative expression is this. Two times x plus 4, x plus 1 to the power 4. Right. Now, take a value for x in this interval. Here, people, this power is 4. 4 is even power, this one. If even power here we have, this is always positive. Even power of a real number is always positive, no? So therefore, in deciding the sign of second derivative, don't go to find the sign of this one, take that as always positive. Only the sign of this you have determined. That sign is the sign of the second derivative. Now we are going to take in the interval x less than -4. Take a value for x, -10 put, -10 plus 4, -6 into 2, -12. Second derivative is negative. Between -4 and -1, put -2. -2 when you put here, 4 minus 2 is 2, 2 and 2, 4 plus. Greater than -1, put 0, also plus. People, now, by the second derivative sign, you can say what? If the second derivative sign is negative, concave down. Concave down. Positive, concave up here, also concave up. We know second derivative positive means concave up, second derivative negative means concave down. Right. Now the last part. Now we draw the graph. Right now, x-axis, this is y-axis, this is negative x-axis. Vertical asymptote is x minus 1 here. Then we have draw vertical dotted line like this. This way. Station point is where? minus 3 minus 1 by 4. Minus 3 is somewhere here. Take minus 3 somewhere here. Minus 2 minus 3. Minus 3 here. Minus 3 minus 1 by 4. The station point's coordinates. Right. There we have a minimum. Right. Minimum graph, no? Right. Now, people, this is how we draw the graph. Now, when we go closer to this line, since at x equals minus 1, we have vertical asymptote, and here we have to have a minimum, right? Then this branch should go like this way. Then only here we can keep what minimum. This line, this branch going like this, it can't turn like this. It can't turn like this. It should go like this. Okay, why? As we come closer to minus 1, at x equals minus 1, we noticed we had what? Vertical asymptote. So therefore, the graph should go closer to that. For this vertical dotted line and this graph become parallel, then they meet at infinity. That is the meaning of the vertical asymptote. Like this graph should be. Like this. Sometimes you might ask, what is this? Having this way, by turning like this, can't it go to negative infinity? This way. No, people. If it goes like this and turning like this, there will be another station point created as maximum. But nowhere in the calculations, we could find such maximum. So therefore, it can't go to negative infinity. So therefore, this branch is wrong if you think like that. Right. Now, to the left of minus 3 people, the branch should be like this. Then only here we will have a minimum shape. But we notice point of inflection is at minus 4. At minus 4, y coordinate is 2 by 9. Like this. Somewhere here. Minus 4 here. Take minus 4. Here minus 4. Here minus 3. At minus 4, y coordinate is people minus 2 by 9. Minus 2 by 9 is above this minus 1 by 4. And now when you draw there, people, here, in this table you can see from minus 4 to minus 1 here, minus 4 to minus 1, from here to up to this minus 4. the second derivative is positive, graph is concave up. That means when you construct tangents from -1 up to -4 region to this graph, people, the graph should lie above the tangents, correct? No? When we construct tangents, people, like this, you can see the graph lies above the tangent. On the left of -4, people, concave down. Then after this point, the graph should be completely concave down, means should be like this. We have to draw the diagram so that at the point -4, -2/9, to the right of that concave up, to the left of that concave down the graph. For that you get marks, right? And then we have to very carefully show that. Like this. Now you can see when we keep drawing tangents on the left of this point, the tangents will be coming above the line graph. So that graph is concave down. Before this one, when we construct, people, right? Before this point, when we construct, what can we say? This way. There. Now, when we keep drawing the tangents like this, people, you can see graph is concave up. And exactly when we draw the tangent here, the tangent crosses the graph. And after that, when we draw, the graph lies below the tangents and concave down. And like this, when it goes, people, this should come closer to x-axis, because at y0, there is a horizontal asymptote. How did you define the horizontal asymptote, people? When we move along the positive and negative x-axis to both ends, negative, positive, infinity directions, the graph should go closer to y0. Y0 means x-axis. Then graph should come closer to x-axis. And especially, people, this coordinates should be mentioned there. Otherwise, you lose 5 marks. This coordinate we have marked here, people, right? And the point of inflection coordinates also you have to mark. It is -4, -2/9. Right? This way, the concave down, concave up also, we have to very carefully show in it to get marks. And the other thing is, people, this branch is coming closer to x-axis, and don't draw that branch to touch this x-axis. The branch will touch the x-axis at -infinity. So don't draw the branch this of the graph so that it touches the x-axis. That part is over. The other part, people, now, right? Other part. Now, on the right of -1, I am going to draw. On the right of -1, people, on the right of -1, gradient negative. Gradient negative means graph should be having this shape, no? Gradient negative means that, no? Right? And on the right of -1, graph is concave up. That means what? When we draw tangents to the graph should lie above the tangents. And also, people, close to -1, the y coordinate of the graph should go to +infinity or -infinity. So therefore, there are 3 conditions for the graph on the right hand side of -1. Graph is concave up. Gradient is negative. When we come closer to -1 from the right hand side, the y coordinate of the graph should go to infinity, plus or minus infinity. To satisfy these 3 cases, people, the graph should be like this, no? Here, graph should be like this. No? When we draw the graph like this, the gradient is negative. When we keep drawing the tangents, graph lies above the tangent, concave up. And when we come closer to -1 from the right hand side, y coordinate going to +infinity, asymptote is there. If you think it like this, people, this is wrong. The reason, when we draw this way a graph, the gradient is positive, but gradient is negative on the right of -1. So therefore, this is not the graph. Right, this is a graph now. And now when we walk along the x-axis to the plus infinity direction, y coordinate should come to 0 because we told at y equals 0 there is a horizontal asymptote. So therefore, the graph should come closer to the x-axis like this. This is the people graph of this given function. And now you can see the graph cuts this y-axis at this point. That point also you have to mention. You know, this point is on the y-axis. No, any point on the y-axis has 0 x coordinate. X coordinate 0. How to find this y value? Come to here. Put x equals 0 in this. When you put x equals 0, this is 2, numerator. Denominator, people, 0 plus 1 is 1, 1 squared is 1, 2 by 1, it is 2. Then this point is 0, 2. This point is 0, 2. People, this is the complete graph of the given function. This is how we draw the graph, right? This is how we draw the graph. Right, no? Okay. Right, people, this is the end of this theory of the curve sketching.